Deep beneath our feet, 2,900 kilometers down, something fundamentally impossible just happened inside Earth's core. In early 2023, geophysicists published groundbreaking seismic data revealing that Earth's solid inner core slowed down and reversed rotation. Media headlines worldwide sparked immediate alarm, warning that the center of our world was spinning backward toward catastrophic chaos. Direct human physical access to the core remains impossible, as our deepest borehole reaches merely 12.5 kilometers deep. To study the inaccessible planetary interior, scientists analyze earthquake seismic shockwaves traveling directly through different deep mantle layers. Beneath our thin continental crust sits the massive, semi-solid mantle layer extending 2,900 kilometers into dark space. Further down lies the outer core, a vast liquid iron ocean running hotter than 5,000 degrees Celsius in perpetual motion. This liquid metal ocean movement generates Earth's magnetic shield, protecting all living surface species from deadly space solar radiation. At the absolute center rests the solid inner core, a metallic ball 2,400 kilometers wide under immense pressure. Despite extreme temperatures reaching 5,400 degrees, intense gravitational weight forces the inner iron ball to remain solid. This solid metallic core rotates independently, decoupled from the mantle by the surrounding liquid outer core's fluid mechanical layer. Analyzing 60 years of repeated earthquake seismic records revealed that inner core rotation speed alters relative to Earth's surface. During the 1960s, the inner core spun faster than the surface, gradually slowing until stopping relatively around the year 2010. Afterward, the solid core began spinning backward relative to us, shifting position by approximately 1 degree each passing year. To understand this relative reversal, imagine passing a slower-moving car on a highway. The slower vehicle appears drifting backward. The solid core is still spinning forward, but slightly slower than Earth's crust, creating a relative backward motion from our perspective. Geophysicists confirm this directional shift is part of a natural 70-year oscillation cycle occurring repeatedly throughout Earth's historical evolution. Heat flow from the core to the mantle drives complex thermal convection currents inside the liquid outer core's iron ocean. Liquid metal motion creates a dynamo effect, generating Earth's planetary magnetic field through continuous electromagnetic fluid interaction mechanics. This magnetosphere deflects harmful solar wind plasma streams, shielding our atmosphere and preserving surface ocean environments for living species. Deflected charged particles are directed toward polar regions, colliding with atmospheric gases to produce vibrant, dancing auroras across high latitudes. Over the past century, scientists observed Earth's magnetic field gradually weakening, particularly across the South Atlantic Anomaly region. Satellites passing through the South Atlantic Anomaly experience heightened radiation exposure, causing electronic glitches in orbital hardware instruments. Historical geological records prove Earth's magnetic poles reversed completely multiple times, with the last pole flip occurring 780,000 years ago. While core slowdowns trigger magnetic intensity changes, scientists confirm this 70-year cycle will not cause an immediate catastrophic reversal. First reason scientists worry: core speed fluctuations disrupt fluid motion inside the outer core, destabilizing our planetary magnetic field. As fluid convection currents adjust to inner core deceleration, the geodynamo mechanism experiences subtle energetic alignment shifts across mantle boundaries. Weakened magnetic field protection allows higher solar radiation doses to penetrate upper atmospheric layers, impacting global satellite navigation networks. Second reason scientists worry: changing core rotation alters mass distribution dynamics, creating measurable microsecond variations in length of day. Gravitational torque interactions between the inner core and mantle transfer rotational momentum, subtly accelerating or decelerating surface rotation speeds. While fractional millisecond day-length shifts seem tiny, extremely precise global navigation, telecommunication grids, and atomic clocks require continuous compensation. Third reason scientists worry: core motion shifts modify deep thermal plumes, potentially triggering long-term volcanic and seismic geological unrest. Altered core convection alters heat dissipation routes toward the mantle base, influencing global mantle plume migration over long geological timescales. Tectonic plate stresses respond to mantle thermal flow variations, causing subtle seismic adjustments along major fault lines over multi-decade periods. Seismologists continue deploying global sensor arrays to track acoustic wave velocity shifts passing through the inner core's metallic lattice structure. High-pressure laboratory experiments simulate extreme 5,000-degree core conditions, studying how solid iron crystals deform under colossal stress. Supercomputer simulations model geodynamo fluid dynamics, attempting to predict future inner core rotational acceleration trends across coming decades. Understanding core mantle coupling mechanisms helps geophysicists separate natural cyclical core oscillations from long-term planetary evolution trends. Despite alarming internet media claims, the core's relative rotation reversal represents a recurring natural feature of Earth's internal engine. Earth's internal magnetic and gravitational engines have operated smoothly through countless 70-year cycles across billions of historical years. Advanced seismic tomography algorithms provide unprecedented structural resolution, mapping precise density variations inside the solid iron sphere. Measurements confirm the inner core possesses structural anisotropy, meaning seismic waves travel faster along its polar axis than equatorially. Differential rotation between core layers causes these anisotropic crystal alignments to shift slowly relative to surface seismic observation stations. Satellite magnetometers track minor geomagnetic dipole drift, linking surface field variations to deep outer core fluid circulation shifts. Global navigation satellite systems constantly monitor millisecond planetary rotation changes, automatically applying leap-second adjustments when necessary. Geophysicists continue debating whether core mantle gravitational torque, or electromagnetic drag, serves as the primary driver of rotation changes. Deep thermal imaging reveals mantle plumes originating directly from ultra-low velocity zones situated at the boundary of the outer core. Continued monitoring of seismic wave doublets provides definitive empirical proof that the inner core's relative movement is slowing down. Surface life remains entirely safe as Earth's vast mantle and thick crust buffer us from deep internal mechanical momentum transfers. Scientific exploration of Earth's inner core demonstrates how persistent observational inquiry transforms alarming anomalies into confirmed natural physics. As observational seismic technology improves, researchers capture unprecedented real-time data regarding the inner core's structural lattice alignment. Deep interior soundings reveal that inner core boundary crystallization continuously releases latent heat, driving outer core fluid convection currents. Convection currents in the liquid outer core act as a giant planetary heat engine, generating electromagnetic energy through perpetual motion. Mathematical modeling confirms that gravitational coupling between inner core density anomalies and mantle structures regulates rotational momentum exchange. Surface geomagnetic observatories log subtle secular variations in magnetic field intensity, connecting core fluid dynamics directly to climate research. Microsecond day-length shifts caused by core momentum transfers are precisely measured by atomic clocks and very long baseline interferometry. Geodynamo stability depends upon balanced thermal dissipation, ensuring Earth's magnetic shield remains active despite internal rotational speed fluctuations. Historical seismic records from nuclear tests conducted in the 1970s provide invaluable baseline travel time calibration data for inner core studies. Variations in inner core rotation speed alter the geometry of magnetic field lines near the core mantle boundary layer over time. Advanced computer simulations combine fluid mechanics, thermodynamics, and electromagnetism to forecast geodynamo stability across coming millenniums. The South Atlantic anomaly's ongoing expansion highlights localized magnetic field weakening, prompting continuous space weather monitoring for satellite safety. core heat flow drives mantle plume ascension, fueling hotspot volcanism responsible for oceanic island chains like Hawaii and Iceland. Seismic wave travel time anomalies confirm that inner core anisotropy is non-uniform, exhibiting distinct hemispheric structural differences deep underground. Continuous calibration of global timekeeping systems ensures international telecommunications, financial networks, and air traffic control remain perfectly synchronized. Gravitational interactions between the Moon, Sun, and Earth's core create complex tidal torques that subtly influence core rotation cycles. Experimental high-pressure physics facilities continue compressing iron-nickel alloys to millions of atmospheres to replicate deep planetary core environments. The relative rotation reversal of the inner core reflects an internal balance mechanism, preventing permanent mechanical or magnetic instability. Satellite geomagnetic missions like ESA's Swarm Array deliver high-precision global field maps, detecting minor core dynamic shifts in real time. Deep interior thermal convection drives surface continental drift over 100 million-year geological cycles, constantly reshaping planet Earth's geography. Understanding the geodynamo's self-sustaining mechanism explains why Earth preserved its protective atmosphere while smaller planets like Mars lost theirs. Seismic doublets, earthquakes occurring in identical locations decades apart, provide precise physical evidence confirming inner core. Movement rate changes. Electromagnetic drag forces generated by outer core fluid currents act as a brake on inner core rotation speed variations. Atmospheric density variations in upper ionosphere layers are monitored continuously to protect orbital space stations from localized solar particle events. Multi-decade core speed cycles demonstrate that Earth's interior operates as a dynamic, interconnected heat and momentum exchange system. Tectonic stress accumulation along major fault lines is influenced by deep mantle flow dynamics driven by core boundary thermal output. Reevaluation of historic geomagnetic reversal events reveals that magnetic field pole flips require thousands of years of gradual structural changes. Advanced seismic tomography reveals large, low-shear velocity provinces sitting deep at the base of Earth's mantle layer above the core. Inner core rotational momentum shifts transfer minute kinetic energy quantities to Earth's mantle, subtly altering total planetary angular momentum balance. High-precision atomic clocks ensure global satellite infrastructure maintains accurate timing synchronization despite sub-millisecond planetary rotation. Speed adjustments. Core heat flow stability preserves long-term geodynamo activity, shielding Earth's surface biosphere from destructive cosmic radiation bombardment over eons. Geophysical studies confirm that the core's relative rotation slowdown poses zero immediate threat to human health, infrastructure, or surface stability. Deep interior seismic soundings continue providing valuable data regarding phase transitions of iron alloys under millions of atmospheres pressure. Core dynamics research bridges planetary geology and astrophysics, helping scientists evaluate habitability conditions on distant exoplanets across galaxies. Variations in geomagnetic field strength are mapped continuously to update navigation algorithms used by commercial aviation and maritime shipping. Gravitational torque coupling between core layers causes periodic shifts in inner core orientation relative to Earth's spin axis over long cycles. The 70-year inner core rotation cycle reflects natural fluid dynamics inside the outer core, operating within expected planetary physics boundaries. High-altitude atmospheric ionization sensors track cosmic ray penetration levels, confirming surface radiation protection remains entirely effective worldwide. Seismological arrays deployed on ocean floors provide critical data regarding seismic wave trajectories traversing the deepest parts of Earth's interior. Continuous research into Earth's internal engine highlights the complex, self-regulating planetary mechanisms that make life on Earth possible. Automated seismic monitoring networks automatically process global earthquake signals, updating internal Earth density models within hours of major events. Geodynamo field line variations near polar regions cause northern and southern lights to alter their visual intensity and geographical distribution over time. Inner core rotational deceleration demonstrates that planetary interiors remain dynamic, evolving systems long after surface accretion processes concluded. Deep interior heat loss drives slow mantle convection, supplying energy to volcanic arcs and subduction zones around Pacific Ring of Fire. Precision satellite altimetry monitors subtle Earth oblateness changes caused by core mantle mass redistribution, updating planetary shape models continuously. Interdisciplinary geophysical research transforms sensationalized internet headlines into rigorous empirical understanding of Earth's deep internal physics engine. Ongoing telemetry from space magnetometers confirms Earth's dipole field remains robust, preserving planetary habitability across coming generations. Advanced seismic analysis techniques resolve fine-scale density heterogeneities within the liquid outer core, refining planetary fluid dynamics models. Mechanical and electromagnetic forces operating at Earth's core boundary demonstrate nature's remarkable ability to maintain long-term planetary equilibrium. Exploring the mysteries of Earth's inner core deepens our scientific appreciation for the hidden physical forces sustaining our living world. Humanity's scientific journey into Earth's deepest interior proves that understanding our planet's core ensures our species' secure future in space. Understanding deep planetary core physics goes far beyond academic curiosity, serving as a critical scientific foundation for Earth's future. Deciphering interior geodynamics improves global earthquake forecasting models, helping seismologists better understand stress accumulation mechanisms within planetary crusts. Comparative planetary science utilizes Earth core data to analyze internal structures of terrestrial neighbors like Mars, Venus, and Mercury. Studying alien planetary magnetic fields guides astrophysicists searching for habitable exoplanets capable of sustaining liquid water and life. Economic geologists map deep mantle convection routes to locate valuable mineral deposits forged deep underground across millions of geological years. Modern geophysicists utilize global seismic tomography, processing vast earthquake data streams with advanced supercomputer algorithms to image Earth's center. High-resolution seismic scans revealed a distinct structural anomaly nestled deep inside the solid inner core, the innermost inner core. Spanning roughly 800 kilometers wide, this innermost metallic core sphere represents a unique remnant phase from Earth's early formation. Scientists theorize this innermost structure solidified first billions of years ago during violent planetary accretion before outer layers accumulated. Direct physical sampling remains impossible, requiring geophysicists to rely on indirect acoustic wave, reflections, and advanced theoretical physics calculations. Over coming centuries, advanced seismic observation techniques will undoubtedly resolve remaining mysteries surrounding deep interior thermal and magnetic dynamics. Beneath our feet lies an extraordinary hidden world. A liquid iron ocean surrounding a solid, white-hot metallic sphere operating continuously. Without this perpetual internal heat engine generating our protective magnetosphere, atmospheric gases would vanish, leaving Earth cold and desolate. Internal core heat drives mantle thermal plumes upward, supplying thermal energy that powers plate tectonics, volcanic eruptions, and continent drift. Sensational media stories claiming the core's relative reversal threatens human civilization ignore decades of confirmed empirical geophysics research data. Core rotation speed cycles represent entirely natural, recurring features of our dynamic planet's long-term internal mechanical balance system. 100 years ago, scientists knew very little about Earth's core structure, completely unaware that it possessed separate liquid and solid layers. Rigorous scientific debate and peer-reviewed verification drive continuous progress, refining our collective understanding of deep planetary physics mechanisms. Citizen science projects enable interested individuals worldwide to contribute valuable local environmental data, supporting professional geophysical observation networks. Engaging young minds with geology and astronomy inspires next-generation scientists who will solve Earth's remaining deep interior mysteries. Billions of years in the far future, Earth's internal core heat will eventually fade as our aging sun expands into a red giant. Until that distant cosmic epoch, Earth's core will continue operating smoothly, protecting our biosphere and sustaining planetary habitability conditions. Deep interior heat rising through the mantle feeds over 500 active volcanoes worldwide, constantly refreshing Earth's atmospheric gas composition. Volcanic activity and tectonic movements recycle vital nutrients and minerals, creating fertile soil essential for sustaining terrestrial ecosystems everywhere. Tectonic plates float slowly upon the semi-fluid mantle, moving mere centimeters per year, driven by deep thermal convection currents. 250 million years ago, all continents were joined in the supercontinent Pangaea before deep core heat drove them apart. Unraveling what triggers core speed acceleration and deceleration remains an active frontier of research in modern planetary geophysics. Earth is not a static rock, but a complex, self-regulating planetary engine operating continuously through deep gravitational and thermal mechanisms. Advanced seismic tomography algorithms construct three-dimensional density maps of Earth's interior, resolving fine-scale thermal anomalies near core boundaries. Crystallization at the inner core boundary constantly releases lighter elements like silicon and oxygen into the surrounding liquid iron ocean. Compositional buoyancy forces combined with thermal convection drive powerful turbulent fluid circulation throughout the liquid outer core layer. Coriolis forces generated by Earth's daily planetary rotation organize liquid iron convection streams into helical, column-like magnetic structures. Self-sustaining geodynamo action transforms mechanical fluid kinetic energy directly into a powerful global dipole magnetic field. Satellite constellations continuously monitor geomagnetic field intensity, mapping localized regional variations across continental and oceanic sectors. High-precision atomic clock arrays detect sub-millisecond day-length changes, providing empirical data regarding rotational momentum exchange between interior layers. Deep thermal plumes rising from ultra-low velocity zones at the core base transfer heat energy toward upper tectonic plate boundaries. Subduction zones recycle oceanic crust into the lower mantle, maintaining long-term chemical and thermal balance across planet Earth's interior. High-pressure laser-heated diamond anvil experiments simulate multi-megabar core pressures, measuring physical deformation properties of solid iron alloys. Anisotropy measurements confirm seismic waves travel roughly 3% faster along Earth's polar axis than through equatorial core planes. Differential core rotation slowly shifts this crystal lattice anisotropy orientation relative to surface seismic recording stations over decades. Geomagnetic field line distortion in polar regions triggers dynamic auroral display intensity shifts during periods of heightened solar activity. Solar wind particle shielding preserves Earth's upper atmospheric ozone layer, shielding surface biology from harmful cosmic ultraviolet radiation. Deep interior mechanical momentum exchange between core and mantle operates within strictly defined conservation of angular momentum laws. Long-term geodynamo simulations demonstrate that geomagnetic dipole field reversals occur naturally following multimillennial structural destabilization phases. Geological evidence from ancient volcanic lava flows confirms life survived multiple past geomagnetic pole reversals without extinction events. Commercial aviation and maritime shipping navigation networks automatically update geomagnetic lookup models to ensure absolute positional accuracy. Space weather early warning systems monitor upper atmosphere ionization changes, protecting satellite constellations and terrestrial power grid infrastructure. Planetary geophysics research demonstrates that internal heat loss rates regulate long-term evolutionary trajectories for terrestrial planets across galaxies. Core rotation slowdown represents a recurring natural feature of Earth's internal physics engine, ensuring long-term planetary stability. Interdisciplinary scientific collaboration continues, unlocking the deepest secrets of our living planet, transforming fear into empirical knowledge. High-precision global seismic arrays process earthquake signals instantaneously, refining internal Earth density models with unprecedented structural clarity. Latent heat release at the inner core boundary drives thermal convection, sustaining liquid outer core fluid motion across billions of years. Liquid metal fluid dynamics inside the outer core operate as a self-regulating thermal engine, preserving planetary magnetic shield strength. Gravitational torque coupling between mantle density heterogeneities and inner core structures regulates long-term planetary rotational momentum exchange. Geomagnetic observatories record subtle field intensity fluctuations, linking deep interior core dynamics directly to atmospheric ionization research. Sub-millisecond day-length variations caused by core momentum transfers are continuously compensated by atomic timekeeping networks worldwide. Geodynamo self-sustenance ensures Earth's protective magnetosphere remains active, preventing atmospheric solar wind erosion over geological eons. Historical seismic data from nuclear tests conducted decades ago provide crucial baseline calibration references for modern inner core research. Inner core rotation speed variations alter magnetic field line configurations near the deep core mantle boundary layer over time. Advanced magneto-hydrodynamic computer simulations model fluid turbulence inside Earth's outer core to predict magnetic shield behavior. South Atlantic anomaly expansion highlights localized field weakening, necessitating continuous space weather monitoring. For orbital satellite hardware protection, deep mantle plume ascension fueled by core heat output generates hotspot volcanism responsible for oceanic island archipelagos worldwide. Seismic wave travel time anomalies reveal structural anisotropy variations between eastern and western hemispheres of Earth's inner core. Continuous calibration of global atomic time standards maintains seamless synchronization for international telecommunications, financial systems, and power grids. Gravitational tidal torques exerted by the Moon and Sun subtly influence internal core rotation cycles over multi-decade periods. High-pressure laboratory facilities compress iron-nickel alloys to millions of atmospheres, replicating extreme physical conditions of planetary centers. Relative inner core rotation shifts reflect an internal mechanical feedback loop, maintaining long-term planetary mechanical and magnetic equilibrium. Satellite geomagnetic missions like ESA's Swarm Array deliver high-resolution magnetic field maps, monitoring deep core dynamic shifts in real time. Mantle convection driven by core heat loss powers continental drift over 100 million year cycles, reshaping planet Earth's surface geography continuously. Understanding geodynamo self-sustenance explains how Earth maintained its oceans and life while smaller terrestrial worlds dried completely. Seismic doublets from identical earthquake sources decades apart provide precise empirical confirmation of inner core movement rate changes. Electromagnetic drag forces between outer core fluid currents and inner core boundary act as a mechanical brake on rotational variations. Atmospheric density variations in upper ionosphere layers are continuously monitored to protect orbital infrastructure from localized radiation bursts. Multi-decade core speed cycles demonstrate that Earth operates as a dynamic, interconnected heat and momentum exchange planetary engine. Tectonic stress accumulation along major fault lines responds to deep mantle thermal flow dynamics regulated by core boundary heat loss. Re-evaluating historical geomagnetic reversal events confirms that pole flips require thousands of years of gradual structural magnetic field evolution.